Our next adventure is moment-generating functions, or MGFs. Here are 3 key MGF facts. Fact 1. An MGF is an expected value. The last 2 facts can be identified from the name, moment-generating functions. So fact 2 is a moment-generating function is a function. Up till now, expected values have only been constants. That's going to change. And 3, moment-generating functions generate moments, which is the purpose of an MGF. Remembering these 3 MGF facts will get you started on the right path. Before jumping into the details, let's review the MGF's notation.
X's MGF is capital M sub-random variable x of little t. You can ignore the random variable subscript, which is common with our notation. Notice the function is in terms of little t, not little x. Little x has been the variable representing capital X's value. However, little t is not little x. In fact, little t has no direct meaning or connection with the random variable. Little t is the variable for the MGF. Its role will be clear shortly. By definition, X's MGF is the expected value of e raised to the t times x. MGFs exist for both discrete and continuous random variables. So, a discrete MGF equals e raised to the t times x times the PMF summed over all x values. A continuous MGF equals e raised to the t times x times the PDF integrated over x's range. Let's think ahead. Consider a discrete MGF. After substituting all the x values and probabilities, all the x variables disappear. But what happens to t? Observe t still exists. The same concept applies for continuous MGFs. That's why the MGF is a function in terms of t.
So, how does this function generate moments? Let's start with the general case, where we calculate x's nth moment.
Find the MGF's nth derivative with respect to t. The nth derivative at t equals 0 produces x's nth moment. Sometimes this evaluation is a limit as t approaches 0 from the right. So, if we review specific moments from the general case, x's first moment equals the MGF's first derivative evaluated at t equals 0. X's second moment equals the MGF's second derivative at t equals 0. In short, calculate x's moments by differentiating x's MGF and evaluate at 0.
This seems like magic. Why does this work?
Observe differentiating an MGF is differentiating an expected value. Since the derivative is with respect to t, the only term to differentiate is e to the t times x. Its first derivative is x times e to the t times x. What happens when t equals 0? E to the 0 equals 1, and the result is x's expected value. If we differentiate again, the result is x squared times e to the t times x. Set t equals 0, and there is x's second moment. In other words, every time e raised to the t times x is differentiated with respect to t, it multiplies by x. Then, evaluating at t equals 0 cancels the exponential term.
That is how an MGF generates moments. As a side note, changing the order of derivatives and expected values is only allowed for certain conditions. Valid MGFs always meet these conditions. Okay, 3 more points.
First, an MGF evaluated at 0 equals 1 because e to the 0's expected value equals 1. Second, Consider the MGF for A times random variable x plus b. The result is e raised to the b times t times x's MGF evaluated at a times t. Now, return to the definition. This MGF equals e raised to the t times the quantity a times x plus b. Create two exponential terms. Notice the bt term doesn't have a random variable x, so treat it as a constant and factor. Now, group a and t. What does this resemble? It resembles an MGF with a times t as the MGF variable rather than t. And that's exactly the result. Third, consider two independent random variables, x and y. What's the MGF for x plus y? Thanks to independence, it equals the product of each MGF. Use this shortcut formula rather than calculating the MGF as the expected value of e raised to the t times the quantity x plus y. Remember, though, x and y must be independent.
That's enough theory. Let's work some examples.
Consider this PDF. Find x's MGF. Then use this MGF to find x's mean and variance. Recall x's MGF equals e raised to the t times x times the PDF integrated from 0 to infinity. Combine exponential terms to produce this integrand. Now here's a cool shortcut. Multiplying by 1 does not change the integrand, so let's multiply the integrand by 2 minus t divided by 2 minus t. Factor the constants, except for the 2 minus t in the numerator. Friends, what does the new integrand resemble? It resembles the original PDF. The point is, the new integrand is another PDF. Recall a PDF integrated over its entire range equals 1. Thus, x's MGF equals 2 over the quantity 2 minus t. If you don't believe that the integral equals 1, prove it yourself. However, the MGF is not valid for all t. Review the integral again. The integral converges to 1 if 2 minus t is positive. Otherwise, the integral does not converge to 1. When that occurs, we do not get a meaningful result. So, preserve convergence to 1 by requiring 2 minus t to exceed 0. Rearrange to create t less than 2, so in all, x's MGF is only valid for t less than 2. Now, calculate the mean and variance. Remember, x's moments are calculated by differentiating and evaluating at 0. Start with the MGF's first derivative. Rewrite the MGF as 2 times the quantity 2 minus t raised to the negative 1. Apply the chain rule to produce 2 times the quantity 2 minus t raised to the negative 2. Assign t to 0 and calculate moment 1. Thus, x's mean equals 1/2. Recall, x's moment 2 is needed for the variance, so calculate the MGF's second derivative. Differentiating the first derivative creates 4 times the quantity 2 minus t raised to the negative 3. Assign t to 0 and calculate x's second moment as 1/2. Since x's variance equals the second moment minus first moment squared, or 1/2 minus 1/2 squared, the answer is 1/4.
As a side note, observe the MGF, both moments, and variance are all nice and neat. This is the result of the PDF. Later, you'll learn how this PDF belongs to the exponential distribution. Now here's a discrete example.
Observe the given PMF. What is x's MGF? By definition, an MGF is e raised to t times x's expected value. Since x is discrete, The expected value is the exponential term times the probability summed over all x values. Substitute known values, and the MGF equals this sum. Simple? We'll now review the colored numbers. Notice anything interesting. What is 0.35? 0.35 is x equals 2's probability. Observe the 2 in the exponent. What is 0.2? 0.2 is x equals 5's probability. Notice the 5 in the exponent. Now examine the MGF for a different random variable, y. Question, what is y's distribution? Here's a hint. Consider x's MGF. Got it? Rewriting y's MGF may help. According to MGF, y's possible values are 0, 1, and 3. All the fractions are the probabilities belonging to the y values. So, this is y's PMF.
Okay, the moral of the story is an MGF hints at a random variable's distribution. When given an MGF, try to match it with the discrete MGF definition. This way, a distribution can be reverse re-engineered from an MGF.